So last time, what did we talk about last time? Statistics, there we go, that's good enough. So we talked about statistics, and we talked a little bit about some of the kinds of observations that we do. So some of the instruments, importantly, the CTD, conductivity, temperature, and depth. Depth is really pressure, and conductivity is really salinity. We want salinity, temperature, and pressure. But that would be the ideal, or salinity, temperature, and depth. But both of those have acronyms that people don't like because they're STDs. So anyway, that was ruled out long ago. But and they're moorings, they're ship base, they're floats, they're satellites, all kinds of crazy things. And then for now, this first paper, you might actually dig into some of that real, like raw data, like the Reed and Mantilla data. But after this paper, we're mostly going to shift into using a reanalysis product, which makes it gridded like a model. You can check balances and the momentum equations and things like that the straightforward way. But because it assimilates data, we know it's as realistic as you can make it with a model with the kind of combining observations and model together. So you can ask real questions with it. It isn't an idealized model, but it's simpler to work with than like random sampled world data sets, which is what I think likely is going to be the conclusion of most of the papers. One is that I don't understand how to use this data set to measure anything because of the observations are so weirdly scattered in time and space. But not to put words in. Okay. So the last thing I wanted to talk about around statistics, which this is actually an update that I just added this time around teaching this class. So if you go to like an AGU oceanography talk, most of the things that we're talking about would be referred to as old-fashioned or coarse resolution or the past. And that has to do largely with, so we talked about robustness and representativeness, that's still a problem. But now resolution is something that people are very focused on. That's true of models, so very fine model grids, but also true of observations. Now people are doing, for surface measurements, meter scale grids over like a 20 kilometer by 20 kilometer by using, all kinds of big data stuff because you can afford to carry around terabytes, collect terabytes per hour easily on a plane or a ship or whatever. So the amount of data coming in is even bigger than what we were talking about now. And that allows you to go to very fine resolution when you connect it together with things like digital cameras, the infrared equivalent, those kind of things. We now have just way better technology. So what does resolution get you? So one of the things that's happened just in my career is the so-called sub-mesoscale. So in the oceans, there's the fine scale, very little stuff. And then there's the basin scale, or kind of like synoptic scale, it sometimes says, like the big scale of like storms and whole basins. And in between, people said, well, the middle scale should be called the mesoscale, right? But then what happens when you add more scales? Well, you get the sub-mesoscale, which is sort of the super fine scale. But anyway, this is sort of kilometer scale variability. And people thought, we're going to talk about eddies and waves and the kinds of waves and eddies that populate this scale, but also other scales as well when we get farther into things. But I just wanted to give you a heads up about this, that like, if you can measure the ocean kilometer by kilometer, it's not like it's boring down there. We talked a little bit about discovering eddies, that they put a pipe, big organ pipe, and it took off faster than they expected in the deep ocean. What happened in the last 20 years or so is that when people got these kilometer scale measurements, they expected to see kind of nothing interesting. There's all kinds of interesting, particularly in the upper ocean. So we'll have a chance to come back to that later, but was a resolution discovery. And then another one that's a little bit older, but it's also important, is you may have already noticed in your homework that the sampling is like every 100 meters or so. Everybody thought that would be what it was like because everyone was imagining these sort of smooth profiles, like from the warm temperature at the top to the cold at the bottom. Actually, if you take a highly detailed measurement with with something that can, there's all kinds of wiggles in there. So what are those wiggles about? That's the fine scale. Some of that is waves, some of that is turbulence, some of that is unknown, but this is another process that's worth thinking about. And so microstructure measurements are one way to try and get at the fine structure. This is a microstructure instrument, which is a very big thing with funny little brushes on it to make it fall in a special way as it drifts down. And then that little teeny tiny thing there is a little sensor that bumps around as the water moves around it, or as the temperature changes, or as the salinity changes. All of those can make these little tiny sensors. And you put those together and you can measure this turbulence on the centimeter scale. And then it's not uniform over the world. So this is a logarithmic scale. So this is like 10 times more than that, 10 times more than that, 10 times more than that, and so on. So people used to think that there was like a background level of mixing going on in the ocean, especially the deep ocean. But now we know that that's not true at all. It's orders of magnitude more over rough bottom topography. And you can imagine like tides kind of sloshing over the stuff on the bottom and making turbulence or something like that. But this also is like last 20 years, totally new perspective on how the oceans work. So we're in the difficult situation, and I want to give you the opportunity to use new data sets, to think new questions, to maybe read some recent papers and write about them. But also some of the stuff we're doing is kind of old fashioned. So you'll notice that tension. It's fine. You don't have to be right to the bleeding edge in your papers that you're writing, but you might find it interesting to kind of motivate the old fashioned versus the newfangled or something like that as a motivating factor for how you decide to structure your papers. All right, sense of people. And we didn't talk at all about measurements in time, but you kind of have the same thing, except you have not only resolution, but also duration. So the resolution tells you about the highest frequency in time stuff, but the duration tells you about the lowest frequency in time you measure. Similar in space too, but we didn't say like the longest distance you can measure is how far you measure. Because it doesn't get that confusing in space, but in time it does. So if you're detecting a climate change trend and you don't have but like a few days of measurements, you didn't detect that trend. You need decades of measurements typically to get anything about climate change. And many of you are going to be excited to use the ECHO data set, which is a couple decades long, to do climate studies with. It's marginal at best. So that's, and for most climate indicators, for some, there's a clear signal, but for others, there's not. So that's something to keep in mind as well. All right. And I have lots of other things. Oh, I will tell you one more thing. The traditional way of managing slow stuff in the ocean that you didn't have access to was to say, well, probably it's the same as it's always been. This is sort of a classic natural sciences thing to do, is like, it's obviously steady, right? Like the earth isn't changing. Like we'll just go measure it and it's been that way forever. Of course, geologists don't like this. They like to think about deep time variations and whatever. But like from the perspective of like, what do you do with the low frequency stuff if you haven't measured it? It's not a crazy thing to think that right now is similar. It's called persistence and weather forecasting. Tomorrow's weather will be the same as today's. And actually, it took about 30 years after the invention of numerical weather models for them to beat persistence skill. So persistence is not a crazy idea. But there's other physical reasons that you might think that that would make sense in oceanography. If the concentration of a substance is assumed to be constant with time, then its rate of input must be equal to its rate of output. We're going to talk about a particular case with salinity today. That's thing, but that's just kind of like inflows and outflows. If more came in and went out, just like a bank account, the amount of that stuff would grow. And then the more goes out than comes in, the money in your bank is going to start shrinking. You're not going to have any savings anymore after a while. So the same idea of a budget is what our main focus for today is, starting to talk about budgets, has that notion. But you can apply that to salinity, you could apply that to sodium, you could apply that to calcium, you could apply that to hydrogen, you could apply it to any element that comes and goes. But they differ because they differ in the amounts of sources and sinks. Some things like iron doesn't really stay in solution very well. So its sink is enormously fast. So if you put iron in on the surface, it basically just doesn't stay in the water, it drops right back out. So it's often a limiting factor because living things need iron to exist. So many parts of the world, what prevents more critters from growing is a lack of iron. And so the residence time is the total amount of stuff that's in your reservoir divided by either the inflow or the outflow, which are going to be equal if you're in steady state. That gives you a time. Like how much, like the amount of salt in Narragansett Bay versus the amount of salt that's coming into Narragansett Bay from, say, the inflow at the mouth. That would be a residence time. And in that case, it would be months, maybe years, but months to years. Okay. So here's some estimates of residence times. So iron has a 200-year residence time for the whole ocean. So all of the iron in the ocean gets replaced every 200 years. But sodium and chloride is 100 million, 68 million years. So there's so much of it already in the salt. Seawater is salty. It's extremely salty. In fact, it's so salty that the sources and sinks of salt are almost negligible until you get out to the million-year time scale or hundreds of million-year time scale. And you can play games with this, like making a periodic table. What do you think the profile of an element would look like if it had a really, really long residence? Like what's going to win in the super long time scale? Mixing. It's going to get straight down because it's just going to mix and mix and mix and mix. And there are no sources and sinks. It's eventually just going to look totally straight down. So some of these you can see have that profile. And you're like, here's sodium, here's chloride, totally straight in the verticals, no distinction between the surface and the bottom. But then, where's iron? We've not taken chemistry in too long. Where is iron? Somewhere over here. It should be one of the curvy ones. I should be, well, here's zirconium. Zirconium doesn't have has a very sharp profile, so it probably has a very quick, short residence time. It comes right out of the seawater if you put it in. And so, and these interesting structures that kind of have these wiggles, you know, like this, have to do with different kinds of sources and sinks. And some places might have lots of sources and others have none. So you might have different representative profiles to kind of represent. Go ahead, Matt. So one of the concepts related, closely related to budgets, we're starting to talk about today, the idea of water masses, which is like a coherent blob of water that's got stuff in it. And these timescales are so long for many of those things that you can actually track a water mass up to thousands of years based on its chemical properties. And so 1,500 years, you can track it that long, and that's actually what we think the oldest water, that is the longest since it was last on the surface, is the ocean. You can even track water masses longer if you're looking at trace constituents that have to do with other more rare sources. Does that make sense to everybody? Okay, so steady state isn't a crazy idea because of all that. And so paleoclimate has lots of other variations, but we already talked about the issue of aliasing and this funny data set that looks like it's crashing, but it's not really crashing. So we got that. Okay, so what do we do with all this data? Just too much. So we put it all together into a model, and then we analyze the model. We pretend that's a lot like the real world, even though we have to be careful to say that it's not real observations. It's a model that includes observations, but you'll get used to saying that. Okay, so I've already mentioned all these other pieces, so let's jump over to today's topic. Are there any other big picture questions about, it's not this? there any other big picture questions about things that we've talked about so far? How do people feel about the level of math and the statistics? Adequate, not overwhelming? All right. How many of you feel really comfortable with calculus? Many? Okay, still a lot of calculus today. And for those of you who don't feel comfortable with it, sorry. You don't actually have to absorb all of the details of the calculus to be able to use the formulas and so on that we're going to build toward and get an understanding. So I'm going to jump back and forth between the way writing it down with calculus and thinking about it like in terms of model grid cells and things like that that are more tangible. So even for those of you who feel comfortable with calculus, maybe this will make you feel even more comfortable with calculus, but there's a bit of tension between how many differential equations I want to show in this class versus how many you actually need to know. And so practice has indicated that people come at it in multiple different levels, but don't feel like you need to track all of the pieces. There should be pieces of this that are new, even if not all of it is new for you. Okay, so budget. Okay, so today we're talking about budget. Next time we will talk about more budgets. That's where we're going for a couple days anyway. Oh, sorry, that was we will eventually talk about ChatGPT when we're getting closer to writing papers and how you can use it, how you should not use it. And more generally, we can have a conversation about whether it's the end of the earth or whatever the people like to say about it. Eulerian versus Lagrangian, that's one thing we're going to talk about, and particularly the material derivative, the control mass and control volume, which if you haven't taken fluids, those terms are probably new to you. Over this time and next time, you'll get to see what they're about. Incompressibility is a key concept. So what's the difference between a gas and a liquid? Compressibility, exactly. But the way that they used to say it was, if you put a container of gas, it will expand to fill its container. Whereas a liquid just stay at the bottom, whatever. So that's one way to think about compressibility is lack of expansion. But also another way to think about it is like how a hydraulic ram works. Like if you fill a hydraulic ram with air, it doesn't work very well because the air just compresses. But if you fill it with oil or water, you can transfer an enormous amount of force because the water won't change its volume as you push on one end and then make it do something on the other end. So that's very true in the ocean. The ocean is mildly compressible. We saw some maps of density before. Maybe it sank in, maybe it didn't. A few percent is sort of the variations in density from the most compressed, deepest, saltiest, coldest to the fresh water, which is about 3% less dense than salty, cold, compressed water. All right. I'm not gonna say budgets again, because you've already heard me say it. Okay, let's see if I can get it, do this well. All right, so this is obviously not a fluid, but it makes a point clearly. Imagine we had some spatial variations in this property, like temperature, salinity, whatever. It's going up and down. And imagine there's a current carrying those spatial properties like this. There are two ways, two categorical ways that you could measure that. You could follow along with the fluid and measure what's going on at your location and then kind of see what goes on. Or you could sit still at a mooring and watch the property go up and down. So those are both useful ways to think about fluids. The follow along with is called Lagrangian perspective after Lagrange. And the sit still is called the Eulerian perspective. Confusingly, Euler actually came up with both of them, but One of them's called Lagrangian, one of them's called Eulerian. Okay, so what kind of an instrument is a good example of Lagrangian instrument that we've talked about? A float, a drifter, exactly. Sometimes a ship if you're not using power. What about an Eulerian instrument? Like a buoy that's fixed, hooked to an anchor, or a ship that's holding station, or a dock, or a satellite. Might also be an Eulerian instrument because it keeps measuring the same place every orbit, even though it's moving. It's not trying to move with the water. It's trying to measure certain latitudes and longitudes repeatedly. Okay? So this one, the Lagrangian perspective, is natural for thinking about conservation because the temperature is staying fixed as you're moving along, you're conserving temperature. Or if the mass is staying fixed as you move along, you're conserving mass. Salinity, momentum, all those kind of things. It's very natural. And so most, if you take physics 100, physics 1, or whatever it is here, I don't remember what the first, physics 70, I don't know. Anyway, you'll talk about cannonballs, lots of things like that. That's a Lagrangian perspective. The mass and the momentum of a cannonball moves with the cannonball. Fine. Sometimes we have a notion of like water parcels, which is kind of a similar idea. But water has a whole lot of different parcels. So you can't easily say, I need to know not only one particular water parcel, I want to know all of the water parcels in order to understand what's going on. So the Eulerian perspective is sitting still and watching it go by. It's natural because it's, if you're lazy, you just sitting still. That's a good way to observe. You just check out what's happening. You don't have to keep up. So conservation principles, observation principles. The budgets that we use most importantly in fluid dynamics relate these two. We want to conserve in an Eulerian frame, or we want to observe in a Lagrangian frame and infer the other one. That's where the calculus comes in. Okay. So you might say, why don't we just do Lagrangian fluid mechanics? It's because of it. How many water parcels do you need to fill the ocean? Like, how big is the water parcel? How many of them are there? They're not atoms. We're not doing that. And they're not molecules. We're not doing that. Something bigger than that, but like how small, it gets complicated. How do you model the interaction? Because sometimes you've got boundaries around you and sometimes you've got other fluid particles next to you. And you have to do different dynamics depending on which was which. And then if you have at least 3 of them, most forces will actually give you chaos and the dynamics of just 3. But we're talking like 300 million, billions, trillions in order to fill an ocean. So it's true that oceans are chaotic in the real world, but we can at least imagine a non-chaotic version of an ocean if we're not trying to follow little water parcels around. There's sort of no non-chaotic Lagrangian perspective on how oceans work. There is interesting examples, slippery sacks. There's a funny way of thinking of it. So if you took like, you filled it up with little slippery sacks that slid on top of each other, and that's one way of doing numerical methods. And then smooth particle hydrodynamics is another way where you make little balls that kind of bang into each other. And you can actually do fluid dynamics with both of those, but it's not very efficient in most cases. Okay, so how do we get from our Eulerian and Lagrangian and how we think about it? The key mental picture is a control volume or a control mass. So control volume, you can think of it as just like a fixed area volume. It could be a cube, it doesn't have to be a cube, it could be, you know, other trapezoids. It could actually be a funny, weird shape. It could be an entire estuary, which is the example we're going to close on today. A control mass, you should think of it as tracking a particular hunk of fluid as that hunk of fluid moves around. I mean, it's this little schematic is meant to be arbitrary dimension, but you know, you could start with something like this and then it wouldn't look like that for very long because it's deforming along with the fluid. So Eulerian perspective, Lagrangian perspective in their barest sense. You also could think about like boxes like this that are moving in time, but they were moving in a kind of specified way, not with the fluid. Or you could think about not material surfaces, but just other random surfaces that were moving in random ways that didn't know that they were holding mass inside. So there's a relationship that we're going to get into a little bit about which speed you change, like which way you deform surfaces or not. Okay, so calculus. All right, so fundamental theorems of calculus. The one that comes up, so this one is the, if you take the integral of a derivative, you get the difference between the endpoints. The way I remember this is there's no shortcuts if you're running uphill. The average slope you're stuck with, doesn't matter what path you take, you got to get from the bottom to the top. Okay? The divergence theorem, I don't have a good analogy, but I think of like a little spiky ball with stuff coming in and out, is the one that says that the divergence of all the stuff in a volume, the divergence being this operator. Does everybody know what del is? Okay. Is equal to the flux of stuff through the outside of the volume. This little delta means the boundary. This means the volume. This means the boundary of that same volume. Okay, so if stuff diverges inside of a volume, then it's going to come through the sides if the volume is fixed in time. And we're going to get into a little bit more what if it's not fixed in time. And then there's a more complicated one called the Stokes-Kelvin theorem that we're not going to worry about now, but we'll worry about when we get to vorticity. But this is the one that says that proves that in my day you can't walk uphill to school both ways. That one goes away in that case. Okay, so we have something that tracks with the fluid, like C called momentum, and we like to make a budget for that stuff. It could be exactly carried by the fluid, or it could just be mostly carried by the fluid, but also like diffusing or receiving heat from somewhere else or something like that. Those are all budgets. To say that something has a budget, a materially conserved budget, doesn't actually mean it is exactly conserved. It means the transport of it by the fluid is important as part of the budget. So we don't want to keep track of the individual parcels. We already decided, so we're going to use something called Reynolds transport theorem, which is a calculus. It's sort of like Leibniz's rule, which I'm going to talk about in a second. And we're going to find this operator to be really important. This is the material derivative, usually written as big D dt. And it's the partial with respect to time. So that's why it has a T down here. It's kind of like a time, but there's also V dot grad of the same thing. So that fluid that was flowing through before, that was going up and down, this is the Eulerian part, the sitting still and going up and down in time. This partial is it's constant with respect to space. So you're taking the time derivative just at a point. This one is the velocity of stuff moving by you. If there are gradients in that stuff, then you see changes. This one is the rate of change you get if you're following the parcels. So you can convert from things that are conserved following the parcels over here into things that are Eulerian observed plus some kind of flow by you. This is the one that's bringing it by you. If there were gradients in the fluid in space, those gradients in the fluid become time derivatives you're conserved. So this is the thing we're going to talk a lot about. We're going to keep coming back to it. Okay, so how does it come from calculus? Does anybody remember the Leibniz rule? It's one of the weird ones. What happens if you take we just talked about, what if you take the integral of a derivative? That's this one. But what if I take the derivative of an integral? The other way around. If I take the ddx derivative of an integral of something where the boundaries depend on x and the thing inside also depends on x, what do you get? You get 1, which is evaluated, the function, the thing that you're integrating evaluated. So this looks like, how do you say that the integral is the antiderivative? So is the derivative the anti-integral is the question. sort of. So this one looks sort of like that. You get the thing inside, outside, but you not only plug in this, you also have a derivative in that quantity. So if that thing was changing, then this would have a multiplier effect minus the other one. So that also looks like the derivative is the anti-integral. But then there's this funny one where the derivative just comes inside and acts inside the integral. So we have two boundary contributions that come from the boundary conditions and one interior. That looks sort of familiar to everybody, maybe not. This one is the motivating one for the more complicated one. It's the one we actually need, which is the same thing, but in 3D. So if I take a time derivative of a volume integral of some property, what do I get? Well, I get the partial derivative with respect to time. That part comes in, and then I just integrate over that. But I also get a boundary contribution, which is similar to these guys. Because this volume isn't fixed in time. So, you know, in some sense, the integrand is a function of time, but so is the boundary condition on the integral. The thing could be deforming, the volume I'm integrating over could be changing in time. So I might get a change. Let's think about this. If I take a box of radioactive stuff, or a balloon of radioactive stuff, it could change because it decays radioactively inside, or it could change because it leaks out of the balloon into something else. There's a boundary where it could change because the boundaries are changing. All of those are possible ways that the amount of stuff inside could change. And so this is kind of breaking all those pieces down. It's important that this velocity in here is not the fluid velocity, it's actually the velocity of the boundary. So we're going to see how that's a little different in a second. Okay, so let's try this out on mass. Okay. I have taken the density of my fluid I'm imagining, and I'm going to integrate it over some volume that might change in time. Okay, you could imagine either the Eulerian box filled with density, or you can imagine the time evolving box, the time evolving mass. Both of them are of this form. What's the answer to this question? What is the time rate of change of a fixed box with fluid passing through it that has different densities of fluid going through? Is that 0? Think of the little sinusoid passing through. Is there a fixed amount of stuff, like at that monitoring station that's going by? You're shaking your head no. There is not, that's right. Because there might be stuff coming through. And so density is like mass per unit volume, and I'm just integrating my mass per unit volume over a volume. But that mass, the density might be changing because stuff, I'm not talking about the same stuff, it's coming and going. I don't know what's going on. So this thing doesn't necessarily change in time. I mean, doesn't not change in time. All right, double negatives. What if this is a control mass that I'm thinking of? I'm keeping track of all the stuff inside, and I'm always going to integrate over to the same amount of mass. What's the rate of change of the density integrated over the volume of that evolving mass? Zero. Because, well, in the radioactive case, I kind of gave you a misleading case. You might destroy the stuff, but right now we're thinking like, what if there's just stuff? There's a certain amount of mass. We're not creating and destroying mass. We're just keeping that mass in a box. And if that mass changes shape, so does the box. And so the time derivative of that would be 0. So this is a useful expression for both our control volume and our control mass cases. And in the control mass case, we're going to expect it to be 0. What about this side? Okay, here's our Eulerian density changing at a point, but it's the integral of it. So I fill my box, whatever it is, with the pointwise change of the density. And then what's this one? Rho V boundary dot the normal direction over the area enclosing my gum. What's that one telling me? What's an example of something that would matter a lot? What's a way? So remember we said this is the time rate of change of mass in our volume. We could change the mass in our volume by changing the density at every point in the volume. That's pretty clear. That's this guy. So that could be my radioactive case. This one is the one that's talking about all the flows in and out of the surface. So what if if it's a control mass, I could follow that mass and make this 0 or not. I could choose not to. I could take an Eulerian flow and let things come in and out of the box. And so V boundary is the velocity between the fluid stuff and the boundary. So either the fluid could be moving through the boundary or the boundary could be moving through the fluid, but in either sense, this term is likely to give you a contribution to how much the time rate of change of the mass in the box is contributing. Okay, is everybody kind of clear on what this equation is trying to say? Okay, so now let's insist on one of our limits. Let's take the control mass case. Let's set the V boundary equal to the fluid. So now it's the velocity of the boundary is equal to the velocity of the fluid. So stuff is not moving out of the box is changing in dimension. Then we said this one was going to be 0. 0 equals that part, which is equal to this guy, just equal to this side. And then we use our divergence theorem here. So we have the divergence of the stuff going through the side instead of the stuff actually going through the side. Oops, sorry, that should be a volume, not a boundary. That should be a volume, sorry. Big typos, critical typos, sorry. That should be a volume and that should be a volume. If that were true, then this would be a volume integral and this would be a volume integral over the same volume. So we might as well put those together. And now I claim that because it's any volume you like, it has to be true not only for the volume, but it has to be true for the integrand. So imagine if there was one little spot where it wasn't true in the fluid, I could just encapsulate that spot and choose that as my volume, and that would disprove this theory, but it isn't. So it has to be true not only in the integrated sense, but for every point in the fluid that this plus this equals 0, which is this. So this is the way of writing the conservation of mass in a fluid without a whole lot of assumptions. It's Eulerian because this I observed just sitting still, and this I also observed sitting still. I'm watching the fluid come and go, and I just need the divergence of that fluid at my point. But it reflects the Lagrangian understanding that if I follow a control mass as it deforms, it doesn't lose or gain mass. So this little bit of calculus plus this divergence theorem has given us a way to write a differential equation that equals the notion of conservation of mass in a Lagrangian perspective. Okay. Is this an easy equation to work with? Yes, like children. There's one really tricky part, which is that density is a property of the fluid, and so is the fluid velocity, and then multiplied together. So that is a nonlinear equation. Rate of change of mass equals 0 is a linear equation. So we, in the Lagrangian frame, our cannonball frame, it's easy to keep track of the mass. In this frame, we have a nonlinear differential equation that keeps track of the mass. So we're going to simplify away and get rid of that in a second. Okay. Let me take the temperature of how everybody feels with this level of calculus. Everybody sort of tracking what's going on? It's terrible that I made this mistake, which is now bothering me. It's going to be on almost every slide from now on. This is the boundary integral. No, this is the volume integral. So let me get back to the divergence there. So it should be this, that this was the boundary integral, and then it becomes a volume integral over the divergence. That's the one I got. Should have been that. Okay. All right, did that one? Okay, now we're totally comfortable with conservation of fluid mass. What about the mass of the salt in the fluid? It's a constituent. So fortunately, we have this concept, salinity. And salinity is measured in grams per kilogram, or the mass fraction. It's how much of the mass is salt versus how much of the mass is water. Okay, so if I multiply density times salinity, what do I get? Density is the mass per unit volume. This is all the mass, everything. And the salinity is the mass of salt versus the mass, salt out, versus the mass in salt. So that product gives me the mass of salt per unit volume. Are you on board with that? So what do I get when I integrate that over volume? Mass of the salt. So mass per unit volume, integrated over volume, I just get the mass of the salt. So now rate of change of salt in the water. Let's take a little blob of water and keep track of the mass of the fluid. Is the mass of the salt also going to be conserved inside our bag of fluid that's evolving as the flow moves or not? The salt mostly gets carried along with the water. Is that part going to be weird for this? It's not, right? It doesn't, if the salt just stays in the water the way it was, and every little water parcel is labeled with the salinity doesn't change, we're just going to get the same game. We're just going to have a salinity factor. It'll be less mass than the total mass, but it's going to follow. That would make this 0. But what kinds of processes, think about it in the motionless case. Like put a salty water in a mess of fresh water and don't let it move, so no currents or velocities. What happens to the salt? It diffuses. The molecules slowly move it along. And the molecules don't count in our fluid velocity. Our fluid velocity tracks the mass of the fluid, not the molecules making up the mass of the fluid. So there should be a little leakage because of diffusion of salt, but there wasn't a diffusion of mass. But we can ignore that and pretend it's still 0. And we could do a similar kind of game with this. So here we have, and see, I got it wrong on this side too. I had the same game. I could just, this is just a Reynolds transfer theorem. Now F isn't density, F is density times salinity. But I play the same game. Push this out, push that through, do the divergence theorem. Say it could work for any volume, whatever. And then now I get this equation, which looks an awful lot like this equation, except instead of density, we got density times salinity. So this is a differential equation, which reflects the control mass idea that salt moves with salty water. It conserves the mass of salt, except for some small residual which has to do with diffusion. So it looks an awful lot like this equation because it is an awful lot like this equation. Except this is talking about the mass of salt and this is talking about the mass of the whole thing, the whole fluid. And I could have played the same game and done it with chlorine. I could have played the same game and done it with energy. I could have played the same game with that. So all of these calculus pieces that we're doing are reflecting a budget of a conserved or nearly conserved quantity. And we're really interested in the conservation following the fluid as it moves around. So we're jumping back and forth between Eulerian and Lagrangian in order to make that work. And well, interestingly, when we do that, we end up with nonlinear differential equations. So we make our life hard briefly. All right. Questions on that? Or I want to jump into some more little manipulations to kind of clean things up. But is that concept pretty clear? And so you could forget all of this. You're not going to be tested on that. But I want you to know why this equation exists and why this equation exists. They are the Eulerian representation of the Lagrangian idea that mass and salt follows the water as it moves around. Okay? Oh, I didn't actually even say vicinity. Sorry. I pulled the whole, F is density times something, sorry. It was S is for something, and then in the next slide, brilliantly, that something is salinity. All right, but anyway, you get the same formula as what we just showed. And in this case, I was willing to neglect the diffusivity altogether and just set that for this. Okay. So we got two equations now. We've got one for density. It looks like this equals 0. And one for salinity, it looks like this equals 0. And they're really similar. Like, look, this is the partial derivative with respect to time. This is partial derivative with respect to time. Sorry, maybe I should be pointing at the one that's going to give away the answer. This is the partial derivative with respect to time of the density. This is the partial derivative of time with the density times salinity. What happens if I take the derivative of a product? Rho times S. That's what? S d by dt of rho plus rho d by dt S. All right, cool. It's a little more complicated with the ones with the divergences and things in them. This guy looks suspiciously like the beginning of the other equation. So this guy, if I take this derivative, one of this is just going to be this guy times S. The same is true for this. If I take the derivative of this guy, it'll be those times S, which is written out here, step by step. So here's rho ds dt, rho v fluid. That's the rest of the stuff inside there. I've now pulled outside and left just the S behind, times this one and that one times S. But what's that thing in brackets equal to? 0.
0 because of this conservation of mass. So I can throw out that term. And so in fact, density, if I'm in the water, the density is not 0. So I can divide through by density, and I have an equation for the conservation of salinity, not just the conservation of salt. And it looks a little different. Looks like this: d salinity dt plus the v outside dot gradient salinity, or material derivative of salinity equals 0. And that's why I brought up that material derivative in the beginning, is because anything that is a mass fraction in a fluid will have an equation that looks like this. So salinity is a mass fraction. You could do energy per unit mass as a mass fraction. You could do entropy per unit mass. You could do momentum per unit mass, which is just another name for velocity. So on and so on and so on and so on. And they're all going to have these material derivatives equal 0 or a small thing, because mostly they track with the fluid, a little bit they don't. Okay? So this guy that I highlighted before is just reappearing here. Okay. Get to this last part. Okay, so here are our two key conservation principles: the conservation of mass, the conservation of salinity, the conservation of salt. Pull out the conservation of mass part, and you're left with the conservation of salinity. Okay, what happens to this equation if rho is constant in time and space? What happens to this term if rho is constant? Zero. What happens to this term if rho is constant? The derivative of a constant times a thing. I can pull the constant out. And then, as we said, if it's not equal to zero, because the density inside the fluid is never zero, I can divide through. So this equation is a decent approximation to that equation if the density is close to constant, which is what we said is true of a liquid. The density is close to constant. It's incompressible. It doesn't compress very easily. So incompressible fluid, conservation of mass, turns out to just be that the divergence of the velocity of the fluid is zero, which is another way of saying the volume of the fluid is conserved. So conservation of mass becomes conservation of volume. They're actually just sort of interchangeable. And once you've done that, once you've assumed that, you can flip these equations all around and do crazy things, because the material derivative of density, there's a correction factor if the fluid is compressible. But if it's not compressible, the density equation starts looking like the salinity equation. And the salinity equation looks an awful lot like the density equation, and it looks exactly like the density equation if the density is constant. So this care that we have been doing to distinguish between this form of the equation, this form of the equation, and the other one, this form of the equation, actually goes away in liquids. And it was sort of like a whole sort of mirage at the beginning that I was doing to try and convince you to think hard about conservation of mass and conservation, rather than just saying conservation of volume. What does that mean about the velocity? So in fact, we're going to be able to simplify things a lot by using this often. And that brings us, this is a weird other thing. It looks cleaner, it looks simpler. This is the same way to get the material derivative from assuming sort of calculus-y things. This one's actually not right, but it's what people show you most of the time. The other one's right. Okay, so that one is, if you want to build some intuition, you can use that. I also put links into the Vallis book, which is like the geophysical fluid dynamics book or atmosphere and ocean dynamics book. You don't have to come back to this, but if this stuff interests you, if you want to get deeper into this and look at alternatives, you're welcome. There's nice descriptions. Okay. So, like I said, we can conserve a whole mess of things like momentum or mass, or salt, internal energy, entropy. We can write little equations for all of them. All of them come from this Reynolds transport theorem thinking. All of them have a material derivative in them. That's the way that fluids work. That's the way that you build fluids equations from just conservation laws from Lagrangian forces. So this is the total set of equations for fluid dynamics. Well, except for what these diffusion and other terms are. There are 9 variables. There are 9 equations for the 9 variables. They are all nonlinear. So it's a mess. What do we do with this mess? We have a mess in the observations, and we use reanalysis. We have a mess in the equations. What do? Exactly. So I could put this in a computer and it could tell me something about these equations. I might not actually be able to use these equations. I might have to discretize them into little boxes rather than having continuous partial differential equations. But that's what we can do. So we have now, if we take our reanalysis products, it takes these equations or a close approximation of them, chops them up into little boxes, keeps track of all the budgets for every little box. We don't track the Lagrangian fluid, but because we're tracking budget and budget and budget and budget from every box to every box, we're getting the equivalent of those flows in and out of control volumes all over the whole fluid. And we don't gain or lose things, because I lose thing out of one box, it goes into the neighbor. Out of one box, it goes into the neighbor. So I can keep track of all the conservation laws that way. All of these equations, except for this one, are of that form. And this one is the equation of state. This is the seawater property. That's what makes seawater special, is how does its density, salinity, and entropy and internal energy relate to each other. There are other ways to write this, which we're actually gonna use other ways, but like this is where it becomes seawater. The rest of them are just fluids with stuff in it, salt in it. That makes sense, everybody? Okay. So let's start thinking about little boxes. You take a little box, we could have stuff flowing in and out in different directions. And then there's stuff inside the box, which, could grow or shrink. And we would just reinterpret these integral equations from our Reynolds transport theorem into flows in and out of the box. And so we can do one for mass, where we say, what's the integral of the density over a volume? Well, that's just the integral of all the density in there. And if we simplify things and say there's just one typical density for that box, it's just the volume of the box times the density in the box. That's a decent approximation to this part. And this one says, well, if fluid is moving in or out of our box on the sides, it might bring some different density with it. And we need to keep track of that. More dense stuff comes in, the density mass inside the box goes up. More lighter stuff goes out, the density in the box also goes up. Lighter stuff comes in, the density goes down. That's what we're keeping track of with this. And writing it as integrals like this, even though we like those differential equations, because this is complicated, like next step of calculus, calculus 2 rather than calculus 1. All of you learned this in kindergarten, but the writing in this integral form is really similar to what we're doing when we discretize. We're doing an integral over little boxes and then approximating things to be just kind of quantities inside the box, exchanging with neighboring boxes. We do the same thing for solids. If we go incompressible, we get even simpler, because now the density falls out of the whole game, and we're just dealing with any volume of fluid that comes in also goes out. Maybe not out of in one phase, it could come in 1 and go out 5, or whatever it wants to do. But that's the conservation of volume, which, if the density is conserved, is the conservation of that. And again, we can write a salinity equation without the density in it. So the density has now been removed from these equations, and where conservation laws, we're just keeping track of the density passive. Okay. So the last closing topic is, what if we take this, apply it not to a grid cell, which is sort of boring, but to like a control volume that's actually like a physical object, like an estuary. So an estuary, like Narragansett Bay, has rivers that are coming and going in one side. It evaporates on the surface on a hot day, precipitates on a rainy day, or maybe a snowy day, whatever. So there's stuff coming in and out. And then at the mouth, it's connected to an ocean. And so it can dump water and other properties that ride along with it into the ocean. And it can exchange that with water coming from the ocean in some kind of exchange flow at the mouth. Or at the sill, I guess, whatever. The shallowest point is where that budget number is. So we got our salinity equation, we got our volume equation. We're going to think about a steady state, not because actual, like Narragansett Bay is in a steady state, but it makes our life simpler because we can just throw away the time derivatives. So here we go. Let's do our volume conservation. Boop, 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 boop. Inflow minus outflow plus the area times the precipitation per unit area minus the area times the evaporation per unit area plus the rivers and other kinds of runoff. That equals 0. That's the fresh water coming and going, conserving the volume, conserving the mass. And finally, we have an equation that's not a calculus equation. This is just algebra. Okay? What about if we do the same thing for salt? What's going to happen? Does salt come and go through the surface? Why not?
Water just evaporates.
Yes, because salt doesn't evaporate. The water, the fresh water comes out, leaves the salt behind. So, or at least to an extremely good approximation, that's true. And rivers are the consequence of precipitation that's coming from evaporation. It just came from the ocean, so it also doesn't have any salt in it because it was fresh when it evaporates, so it's fresh when it rains. And the rocks over here do leak a little tiny bit of salt, but it's a very small effect. We saw that the time scale of ocean salinification is 100 million years. So rivers are essentially fresh as well. What about over here? Is there salt coming in from the ocean? Yes, salty water outside. What about the water going out? There is. Why?
Because there's salt with.
Exactly. There's salt going both ways. Even though these are all fresh, some salt from here is making its way back out. And in steady state, the mass of salt going in has to equal the mass of salt going out in some sense. Okay? So that's what our salt budget is. Inflowing mass of salt equals outflowing mass of salt. Okay? This is a blurb in where we just said more about salt is actually conserved in seawater. It's close enough to true. We already talked that through. Okay, so we have two equations. What kind of equations are those? Not calculus, no derivatives. We've gotten rid of the derivatives. We're back down to the things that are easy to measure with. How many, like, what's an unknown and what's a known here? Like, we don't really know. We have to decide what like a problem we might want to solve. Both of these equations will be true if it's a steady circulation. So maybe we have good observations of precipitation and evaporation in rivers, but we don't have good observations of the exchange flow. But we do have observations of the salinity going out and the salinity coming in. That would be a set that we could manage with these two equations. And in fact, that's what these two are. These are called the Knudsen relations. It's Knudsen in 1900 figured this out. The inflow is the freshwater source and some kind of complicated factor of salinities. And the outflow is the freshwater source times some other factor of salinities. They almost look like they're the same, but is it true that the inflow will equal the outflow? Yeah, why not? Sometimes it's not, but what here tells us that sometimes it's not. This one does, right? These are only equal if there's no net precipitation minus evaporation and no river runoff. Forget this part. If there's river runoff, the outflow had better be bigger than the inflow. Right? When is there a lot of inflow? Just staring at this. There's a lot of inflow if there's a lot of fresh water, maybe. That's a little weird, but we'll come back to that. What about this ratio? When is that really big? How do I make this S naught divided by S that's in minus S out? How do I make that big? I can't make it big by S out because S out is in the numerator and the denominator. So if I make it really big, this just goes to -1. Well, what else can I do? I can make these salinities really close to each other. If they're really close to each other, I'm almost dividing by 0, which means that my inflow is going to be a huge multiple of the freshwater source. Similarly, The outflow, which has the same denominator, is going to be a huge multiple of the freshwater source. So let's look at two nice marginal seas or estuaries, the Mediterranean and the Black Sea. And they differ in exactly that kind of way. We go to the Mediterranean and we make measurements. The salinity coming in actually should be at the bottom. Sorry, the salinity, right? This is weird because the VI would be backwards here. Saltier water goes out, then comes in. And the salty water going out is only 1.5 parts per thousand more salty than the one going in. So that's very close salinities. Whereas in the Black Sea, the salty stuff coming in is twice as salty as the stuff going out. So if you plug in a few other numbers that you might be able to observe, so suppose the fresh water is this number. So it's net evaporation wins out of this. Evaporation is the biggest of river plus precipitation. Actually, in the Mediterranean, you make salty water, you remove fresh water from evaporation, so you get a number, 10 to the 4 cubic meters per second, which we'll start to think about how big cubic meters per second are later. But anyway, that's a pretty substantial amount. That's like tens of thousands of swimming pools per second. So that's pretty big. So what about these two formulas? What are they going to tell us? This is close. So the inflow, 1.75, whatever that is, 10 to the 6 meters cubed per second. 100 times more inflow than evaporates, net evaporation. And similarly, 100 times more outflow. So there's a huge amount of exchange at the Straits of Gibraltar, which you can think of as being either that there's a whole lot of evaporation, that's true, but that evaporation is multiplied by the fact that these two salinities are close. So what's going on in the Mediterranean that makes these salinities close? Like this thing is just jumping force, is taking pure fresh water out and leaving a little bit saltier water behind. How do you get those two to be close? Very close to the right. Rivers. So rivers will be fresh. You got to mix those in too before they make their way out. So how do I take fresh water from rivers, salty water from the atmosphere, and a modestly different exchange flow, kind of an intermediate salty water? How do I make those all one saltiness? Yeah, so there's a lot of mixing in the Mediterranean. So, which is the way that we get to relatively modest salinity differences, starting with fresh water and pure brine rejected water, both of which are, on the extreme ends of the spectrum. We've got to be mixing a lot because the inflow and outflow are almost the same. So this rate of overturning, if you like, is something about talking about the mixing efficiency. You get more overturning if you're mixing a lot. You're going to get less if you're mixing a little, which is the example of the Black Sea. So at the Bosphorus near Istanbul, there's salty water going in, fresh water going out, a lot fresher than saltier. And so this one is 10 to the 3. This one is 10 to the 3, or maybe 10 to the 4 if you include that one. And the fresh water is also a half 10 to the 3. They're all the same size. So in the Black Sea, the fresh water from the rivers basically just goes out. This is almost the same size as that. Or if you like, half of it comes from the rivers, half of it comes from the Mediterranean, and then it goes in. So it's totally balanced, whereas the fresh water was 1% was the evaporated fresh water, and the Mediterranean is 50% here. That makes sense? So even from very simple things, that we take this idea that there could be a budget, you think hard about what would be the math that gives you the budget, what do I have to think about? I need to think about inflows and outflows, and maybe rate of change inside. But in this case, the rate of change inside, we just assume it's zero. Inflows and outflows, do some algebra. You can do real oceanography. This is actually valuable stuff. You can talk about pollution this way. Like, is pollution a bigger problem in the Black Sea or the Mediterranean? What do you think? Yeah.
The
Yeah.
Mediterranean just keeps shuffling the water out.
It keeps diluting it. There's this huge overturning, this big exchange that's coming in, flushing out. It's also bigger volume, so you'd have to proportionally pollute a lot more. And then the Black Sea is small, there's not a lot of mixing. And a lot of the world's most polluted rivers are emptying into it in addition. So it's a very highly pollution-centric place. And we just got to that environmental consequence with less than 2 hours of conversation about basic principles. So hopefully this is where we want to go. The oceanography over and over again. How do we get to really interesting, useful takeaway messages about the way that the environment, climate change, but coming back from like first principles and getting all the way there over and over again. That's the goal. All right, cool. See you next week. Next week, we're going to start talking about topics in Winch chapter 3. Hopefully you've got your books. Okay. We're going to take a very long time in Winch chapter 3, moving to the dynamics section. So skim, take your time sort of absorbing what's in there. That's going to occupy us for a few weeks.